This video deals with the shift of position of the pivot point while handling ships. We will see that existing theory, although simple to remember and handy to work with, fails to explain a few limit cases. I will try to demonstrate that other basic physical principles explain better the movement of the pivot point along the ship's axis in various situations. It will also promote the idea that evaluating the effect that a sideways force has on the rotation and on the lateral movement of the ship is more practical at all stages of ship handling than strictly dealing with the pivot point. Let's start with well-known situations. Our small-scale model will turn around an open dock. When a third of the ship will be clear of the corner, the ship will kick ahead on a hard-to-port wheel. As we have all learned, the ship clears the dock since the pivot point is about 1/3 from the bow when moving ahead. Here is another example. In the next situation, the ship is moving astern. Since my homemade model was too basic to be fitted with a bow thruster, I simply use a string to give an efficient side thrust as necessary. The pull is given when a third of the vessel is clear of the dock. So far, so good. The classic pivot point theory does perfectly well. Now watch our ship going astern and having a very effective stern kick to port. A third of the ship clears the dock. Kick. Ouch. Now going ahead and having a very efficient bow thruster action. Once again, it's not going as per plan. Let's try a different type of efficient underwater thruster. Where is the pivot point? It is lying at about 75% of the ship's length, so 1/4 ship's length from aft. From the last 3 examples, we can see that the classic pivot point theory has its limitations. I will try now to introduce a different approach of the pivot point. But before we do, let me show you the detail of my highly sophisticated homemade bow thruster. Of course, in most of our rivers, it would not be very practical. When you apply a side force on a ship, anywhere along its length, it does not only cause the ship to rotate, it also makes it move sideways. Therefore, it cannot be compared to a body with a hole in its axis through which a spindle is passing. A ship is not pivoting around a fixed axis. Let's start by making a clear distinction between the center of lateral resistance and the apparent pivot point. The center of lateral resistance of a vessel is that point where, if you apply an effective lateral force, no rotation, if the vessel has a steady heading, will occur. Acting on this point, a lateral force has no arm lever, therefore no turning moment. It only pushes the vessel sideways. A force acting ahead of the center of lateral resistance will rotate the ship in a different direction than the same force acting astern of the center of lateral resistance. The lateral resistance can also be called hydraulic lift. The position of the center of lateral resistance is function of the center of the underwater surface area, the center of gravity, and the fields of pressure around the hull. The starting point of the center of lateral resistance is the center of underwater surface area, which is normally close to the center of gravity of the ship. The position of the center of the underwater surface for one ship is mainly affected by the trim. A trim by the stern moves the center of lateral resistance point more aft. A trim by the head moves it more forward. We can see that the apparent pivot point of a ship trimmed by the head with headway is more forward, and the apparent pivot point of a ship trimmed by the stern with headway is more aft. The field of pressure, bow wave, and the stern sub pressure under headway shifts the center of lateral resistance towards the area of higher pressure. This is mainly due to the positive pressure built around the bow in the forward motion, which creates a more resistant surface for the hull to lean on when pushed sideways. For practical ship handling purposes, it seems that the shift of the center of lateral resistance due to the speed is rarely more than 10% of the ship's length in the direction of the ship's movement. The apparent pivot point only exists when the ship is rotating. The position of the apparent pivot point at a given moment depends on the hull underwater resistance to lateral movement and the efficient lateral forces applied on the vessel. In order to estimate the position of the apparent pivot point, we must assess how a lateral force will affect the rotation of the vessel, the sideways movement of the vessel. Let's suppose that you have a bar-shaped body at rest in space and you apply a lateral force on it at one end. The resulting motion can be decomposed in two parts. First, a sideways bodily motion. Secondly, a moment of rotation about the center of gravity. These two results, when combined, will cause a change of position of the body after the force has been applied for a period of time. We realize that the part of the bar that has not changed position in space, P, pivoting point, is not located at the center of gravity but some distance off it, away from the end on which a force is applied. The position of the acting lateral force. A lateral force acting away from the center of lateral resistance will, for the same angle of rotation, push the center of lateral resistance relatively less sideways than a force acting closer to the center of lateral resistance. This results in an apparent pivot point further at the opposite end of the vessel. The closer to the center of lateral resistance the force is acting, the further away to the opposite end the apparent pivot point will be. This can even result in a pivot point outside of the vessel physical limits. Lateral resistance. As we have seen earlier, the lift is the resistance of the water to any lateral movement of the vessel. The hydraulic lift varies with the shape of the hull. A more profiled, narrow hull will induce more lift. Let's compare two ships with the same length, same draft, the first having only the third of the beam of the second one. After the ships have developed sideways motion, it is harder to stop the drift of the wider ship, 3 times heavier for approximately the same lateral resisting force. That resisting force being here the surface area of the wall of water, which is represented by the ship's length times the draft. The underkeel clearance. Little underkeel clearance means more lift. The narrow space under the keel makes it difficult for the water to flow from one side of the ship to the other, so it is harder to push the ship sideways. A higher lift means a pivot point closer to the center of lateral resistance. For the same change of angle, the center of lateral resistance of a vessel with high lift will drift less sideways than a vessel with a low lateral resistance. This results in an apparent pivot point closer to the center of lateral resistance for a vessel with high lift than the vessel with low lift. We can see that the same effect is present when the ship has headway, first in deep water, now in shallow water, in this case 1 centimeter under keel clearance, which corresponds to about 1 meter with a real-size ship. The apparent pivot point is closer to the center of lateral resistance. Motion of the ship after the lateral force have been applied. The rotation effect. Let's take a ship-shaped body, free to move on an air cushion. Let's push it sideways with some anti-clockwise rotation. Now stop the force acting on it and watch the resulting movement. The center of gravity is moving to the right, and the bar rotates around it. The point that has no speed, having for reference the surface, is P, the apparent pivot point. When a ship is being handled at low speed, when the pressure fields on the hull are actually very low, it is mainly due to the rotation effect that the apparent pivot point seems to move astern if the vessel is moving astern and turning, and ahead if the vessel is moving ahead and turning. The other factor affecting it is the ship-generated sideways current. Let's consider a ship turning and moving ahead. The sweeping movement of the stern creates a vacuum which in turn drags a mass of water towards the quarter ship side. The outer ship side also pushes a mass of water away. We will call it the ship-generated sideways current. Let's now stop the force creating the turning movement. The ship, with its rotational inertia, keeps on turning, but the rate of turn will reduce due to water friction. The ship-generated sideways current, with its own inertia, will catch the stern and continue to push it sideways, while the forward part of the ship is in undisturbed water. This force, acting more or less sideways on the stern, contributes in moving the apparent pivot point more forward. All factors stated above have been explained separately. In real life, they all combine together with various intensities depending on conditions. Quantifying precisely the resulting effect for every specific condition is far beyond the best mariner's abilities. But understanding these basic principles and knowing that they fit with reality may be of some help in everyday ship handling. Some real-life observations and how they meet theory. The ship-generated sideways current has a lot to do in the stern seeking to go upwind ability of a ship going astern. The ship adrift is pushed sideways in a beam wind. Its motion creates a ship-generated sideways current. When the vessel is going astern, it pulls the aft part of the vessel out of the ship-generated current. The stern being now in an area of relatively undisturbed water, the rest of the vessel still in the local ship-generated current, A turning couple is created, bringing the stern upwind. As the stern is progressively directed into the wind, it gets out of and produces less ship-generated sideways current. Another force couple is developing. The component of the propeller pull, which is directed in the opposite direction of the wind, is increasing. It creates an arm lever of a length d between the propelling force and the center of windage. As the component of the force increases, when the stern is nearly upwind, the lever distance d decreases. It is why ships will normally find an equilibrium angle a little bit off the wind, especially for ships having large stern accommodations. Another demonstration of the sideways current. The ship is pushed sideways by a tug and its own azipod propeller. The ship creates a side current. A short kick ahead is given to get the bow out of the created current. The stern is carried by the current, causing a turning couple. This time with sternway. This phenomenon was described in 2001 in the text Unpredictable Behavior, example of a reason to reconsider the theory of maneuvering for navigators by Captain Max J. Van Hilten. Donkey, because it describes the behavior of a ship pushed sideways by a forward escort tug, turning against the tug directing force. Initially, the ship is moving ahead. The forward escort tug will start pushing in order to direct the bow to port. The tug pushing has the following effect on the ship: a sideways motion of the ship to port, a rotation of the ship to port since the force is acting forward of the center of lateral resistance. By this sideways motion, the ship is also displacing a mass of water sideways with her, pushing it on port side, sucking it on starboard side. As the ship moves ahead, the bow will float in an area of relatively undisturbed water. The stern, instead, will be affected by the ship-generated sideways current that has started to develop, causing a turning moment that will reduce the port swing and can even initiate a starboard swing. When the ship starts a starboard swing, the stern, due to the rotation, keeps on generating more sideways current than the forward part of the vessel, thus amplifying the turning moment. The rudder of the ship is kept amidship all the way. For those who believe that the tug's drag is the main explanation, I invite you to watch closely the next experiment. Here is a live example of this effect. Even without a tug, with a single pull from a string, the phenomenon exists. A force acting closer to the center of lateral resistance will have a quicker effect since it produces more sideways current. Once again, slower. Watch the shadows of the eddies following the starboard quarter of the ship. We can visualize how it acts unevenly along the hull, having more effect aft than forward, and thus creating the turning couple. This phenomenon can also happen when moving astern. It is more likely to happen with the tug at the accommodations facing than at the forecastle break, since the force is acting closer to the center of lateral resistance. The azipod propeller of the ship was adjusted to produce nearly zero transverse thrust. For this phenomenon to happen, the following conditions must be present. The tug must be powerful enough and its action must last long enough to create sufficient side movement. A sufficient speed through the water is also necessary in order to get a significant part of the hull out of the ship-generated sideways current in a relatively short period of time. The poor turning effect of the bow thruster when moving ahead and its good steering properties when moving astern are well-known facts. A very interesting article on the efficiency of the bow thruster was published in a Nautical Institute book entitled Pilotage. In this article, Captain H. Henson explains that when the ship starts moving ahead, the high-speed stream of water expelled from the thruster bends along the hull. Its high-velocity flow creates a low-pressure area that pulls the bow in a direction opposite to the side we want to thrust it. The result is that the two forces tend to annihilate each other and the net thrust force is very weak. The bow thruster is simply losing its efficiency as the ship moves forward. The loss of turning effect has therefore little to do with the change of arm lever distance between the thruster and the center of lateral resistance. When the vessel is moving astern, the vacuum effect created by the thruster is much less significant since the hull area over which it acts is quite smaller. A light ship is usually trimmed by the stern. Its center of lateral resistance is relatively more aft than a loaded ship. This results in a shorter arm lever from the rudder to the center of lateral resistance. At first glance, this should lead to less steering efficiency. This short arm lever is overcome by the small inertia of rotation of the light ship. Less mass to control, therefore quicker reaction, for approximately the same steering power. On loaded ships, the larger inertia of rotation, even if the rudder center of lateral resistance arm lever is longer, makes the ship slower to react. The following phenomenon can also complicate steering control, especially when some vessels are even keel or trimmed by the head. Let's take the example of a vessel moving north and initiating a turn to starboard. Once the turn is started, the center of gravity of the vessel has now a new direction, a bit to the left of the initial course. Because of inertia, the center of gravity wants to keep going that way. Meanwhile, the vessel itself has a different orientation. Let's say 030. The more important underwater area ahead, combined with overpressure around the bow of these ships, bring the center of lateral resistance well forward of amidship. This means that relative to the new direction of the center of gravity, the center of lateral resistance would be some distance d off to the right. That distance corresponds to an arm lever that can be high enough sometimes to accelerate the rate of turn even with the wheel in midship position. Steering such a ship is like trying to keep the arrow of a wind indicator tail in the wind. On the contrary, when the center of gravity of the ship is forward of its center of lateral resistance, it improves its directional stability. Azipod-driven vessels going astern and turning will best demonstrate the present theory. Their high side thrusting capacity will show a pivot point forward of amidship, even if the vessel is going astern, especially at low harbor speeds. In fact, I foresee the greatest usefulness of the present theory for those who handle azipod and Z-drive ships. The lateral movement of the vessel is only affected by the lateral components of the forces acting on the ship. The center of leverage for lateral forces acting on the ship is the center of lateral resistance. The center of lateral resistance, initially between the center of gravity and the center of underwater surface area, shifts towards aft with a trim by the stern and towards forward with a trim by the head. The center of lateral resistance shifts progressively forward as forward motion through the water increases, progressively aft as aft motion through the water increases. Once the position of the center of lateral resistance is estimated, estimate the relative position and effectiveness of the lateral forces involved. Consider the arm lever length and estimate the amount of rotation and the amount of side movement the force will induce. You can then estimate where the apparent pivot point will lie. The apparent pivot point is a consequence of these two movements combined. It is not a cause. It has nothing to do with the turning arm levers acting on the ship. A ship with high lift will develop less sideways movement. Once a ship has developed a swing and no more force is acting on it, especially at low port operation speed, the rotation effect and the ship-generated sideways current are the main factors determining the position of the apparent pivot point, which is towards the end of the ship going in the direction of the turn.